We want to solve systems of equations, and we want to graph and solve systems of linear equations in two variables, and we also want to use algebraic methods to solve linear systems. So a system of equations is two or more equations with the same variable, and usually we talk about x and y. To solve a system of equations, find the ordered pair that satisfies all the equations, the point of intersection. So graphically, we've talked about there being a point of intersection, and then at that point, we'd have one solution. We also talked about infinite solutions and no solutions. So if there's no solutions, that means that the graphs are parallel, so they have the same slope, but they have a different y-intercept. If they're infinite solutions, that means that they're the same lines, or overlapping lines. If there's one solution, then they're going to have two different slopes and possibly two different y-intercepts, but not always. So that's what it looks like graphically. When we look at it algebraically, we want to see what that might look like when we go to solve. So here we have three examples. So here we have three examples. And as we can see in this one, we have the same slope. Both the slopes are equal to 2, but we have different y-intercepts. So we can, in this case, we can use substitution because they're both equal to y. So we can say 2x minus 4 is equal to 2x plus 3. So we set them equal to each other because by the transitive property, they're both equal to y, so they have to be equal to each other. And then we can solve to get one variable by itself. So we subtract 2x from both sides. And then we get negative 4 is equal to 3. And at this point, we should know negative 4 does not equal 3. But we could do one more step, and we could add 4 to both sides. And then we get 0 is equal to 7. So if we get 0 is equal to a number, or we get two constants that are equal to each other, we should know that this is not true. So in this case, we'd have no solution. We can do the same thing again. We have two expressions that are both equal to y. So by the transitive property, we can say 2x minus 4 is equal to 2x minus 4. And then we can solve that again to get to see what x is equal to. So we add 4 to both sides, and then our 4's cancel, and then we're left with 2x is equal to 2x, and subtract 2x, and then we get 0 is equal to 0. So in this case, 0 is equal to 0. That is always true. So in this case, we have infinite solutions. And then the last example we have here, again, these are both equal to y. So by the transitive property, we can say 4x minus 4 is equal to 3x minus 3. And so we can add 3 to both sides of the equation. And then we get 4x minus 1 is equal to 3x. And then we could subtract 4x from both sides. And then we get negative 1 is equal to negative 1x, and divide by negative 1, and divide by negative 1. And we get 1 is equal to x. So in this case, we have three completely different answers. Here we have 0 is equal to some constant, so that will never be true, no solution. We could end up with 0 equals 0. In that case, that would be infinite solutions. Or we could end up with a variable is equal to a constant, and at that point, we're going to have one solution. But in order to find that solution, we have to take our 1 and substitute it back into x to figure out what y would be. But if we have a variable equal to a constant, that means that there's going to be one solution. So what do we notice about the slope? Well, in this case, the slopes are the same, so they have the same slope. And we notice that the y-intercepts are different. And then for infinite solutions, what do you notice about the slope? Same slope. And what do we notice about the y-intercept? Same. And then for one solution or intersecting lines, what do you notice about the slope? They have different slopes. And what do you notice about the y-intercept? That's also different.